Hello everyone, welcome back. We were somewhere in the middle of derivation of equations for method of characteristics. We started with this matrix. We went to mathematicians, they looked at it this way basically. They looked at the matrix and said, if you solve for phi xy and if phi xy's solution comes out to be indeterminate form, then you can simplify the expression where this coupled differential equation system of second order will now become independent first order differential equations, which is what we wanted to try. And to solve for phi xy, we used the Cramer's rule and we got to this form. Determinant of that matrix with the center column replaced with that side, and the bottom will be just determinant of this matrix. And for this to be indeterminate, we should have denominator 0 separately, numerator 0 separately. Okay. And we looked at this part, it should be of the form 0 by 0. We did this part separately already. We did this and said when the denominator equal to 0, this corresponds to, we said, characteristic directions we said there are two directions, theta plus mu and theta minus mu, for which this will happen. This is what was done up to last class. Okay. From now on we will continue with the numerator getting to 0. Okay. If you look at the numerator determinant and we want to make that 0, if I let us say I will pick the center line and do determinant based on that. A determinant for numerator is equal to, is going to be d phi x times a dy minus d of phi y, times this determinant which is minus c dx. So that minus will just go away and becoming plus c dx, and I am forcing it to be equal to 0. And I am saying it has to be 0 because I am looking at this phi xy indeterminate form. Okay. So I am getting this form. Now we will simplify this a little bit. We will rearrange it such that d phi x and d phi y terms are on one side and dy and dx terms are on the other side. If we do that, we will get to a form d phi y by d phi x is equal to minus a by c dy by dx. Okay. Now we remember our a by c, a and c from our original differential equation. You can go and substitute it back in terms of u and v. Okay. But before that I want to look at this dy by dx. This dy by dx, we already found that from the denominator being equal to 0, I should have two solutions for this dy by dx. Only along that particular two directions the denominator is 0, and if I satisfy this equation then the numerator is 0. So ideally I have to say use that dy by dx here, those two values, and I will get a particular relation here. What is this relation really? This is equal to dv by du, right, because phi y is my v, phi x is my u, small u. Okay. So now the next thing we want to do is go and substitute that particular dy by dx here, but I want to not use that tan of theta plus minus mu value there, I will use one step before, okay, in terms of u and v. So I will write dv by du equal to this a and c I will write here, these are my a and c values. Now inside I will write the expression we wrote for dy by dx in terms of u and v, so that things are getting simpler. That b square minus 4ac term we got it to be m square minus 1, we will keep it that way. Writing it in this form so that I will get rid of this term. So only thing remaining, we will now again substitute u equal to capital V cos theta and v equal to capital V sin theta. I will use this substitution again and we will go back and write this every v and u there like that, v sin theta, d of v sin theta, it is dv divided by d of v cos theta. This is equal to, you know how it comes out, there is going to be capital V square coming out from here, capital V square by a square is my Mach number square, and remaining will be cos theta sin theta. So I will write that whole thing together, it will be m square sin theta cos theta plus minus square root of m square minus 1 divided by, I have sin square m square sin square minus 1, okay, and there is a minus sign here, so I will put that inside here, it will become 1 minus m square sin square theta. I got it to this form. Now I still have this d of v sin theta. Now v can vary, theta can vary, so I will expand this again further, okay, and rearrange terms again. Okay. How will I do this dv sin theta and dv cos theta? I will just put it here, it will be dv times sin theta plus cos theta v cos theta d theta, v cos theta d theta divided by, similarly I have to do differentiation by parts again on this one, dv cos theta minus v sin theta d theta, this is what it should be. Okay. Now I will cross multiply this denominator with that and this denominator with this numerator, and then rearrange terms such that all dv terms are on one side and all d theta terms are on the other side. Okay. If we rewrite it that way, I will finally end up with d theta equal to dv by v times m square minus 1 sin theta plus minus m square root of m square minus 1 multiplied by cos theta. Square root is not for cos theta there, divided by cos theta plus minus square root m square minus 1 sin theta. This is what I will end up with. Okay. Now if I look at it, I am having plus minus in the numerator and in the denominator. How did this come up? I am having a plus minus here, and there is one term which will have a dv with plus minus, other term will have d theta with plus minus, and remember when I put a minus d theta multiplied with this, it should become minus plus, plus minus will become minus plus, but when I rearrange it to the other side of the equal to sign, it will again become plus minus. That is how it got to be plus minus in the numerator and denominator out there finally. Okay. Now this actually means that when I have one particular solution dy by dx, there were two solutions. We said that one solution was, actually I will write both the solutions together. We had this two solutions. If it is theta plus mu dy by dx is equal to theta plus mu, then I have to use the plus here and the plus here. If I have theta minus mu here, then I should use the minus here and the minus here. I cannot have four combinations of this plus minus. They are coupled. If there is plus there, this should be plus. If there is minus here, this should be minus. That is the only way I can use it. Okay. So, because of that, what we are ending up is with two different differential equations in terms of d theta and dv. Okay. That is what we are ending up with finally. Now, we will simplify this a little bit further. If I look at it, there is m square minus 1 here and square root of m square minus 1 here. I can pull out a square root of m square minus 1 common. We will do that. I will get square root of m square minus 1 dv by v into square root of m square minus 1 sin theta plus minus cos theta divided by cos theta plus minus square root m square minus 1 sin theta. This is what I end up with. Now, if I look at it, numerator and denominator are almost the same, okay, except for, okay, let us split the terms now. If I have a plus there and a plus here, they are exactly the same terms. Okay. So, now I can write my expression as d theta equal to square root of m square minus 1 dv by v into one solution is plus 1, right. What about the other solution? If I look at it, if I put minus here and minus here, numerator will have just a minus the square root sin theta minus cos theta, denominator will have cos theta minus square root sin theta. So, this will give me a minus 1. I will have a plus 1 or a minus 1, two solutions. This we typically write instead of like this, we will write it as multiply this with plus minus 1, where now we have to again think back, dy by dx having tan of theta plus mu corresponds to this plus 1 here, and dy by dx corresponding to tan of theta minus mu corresponds to this minus 1 here. Okay. So, those are specific relations we are getting for those two directions. So, now there is one more thing I have to do. This is from some class long back we did in Prandtl-Meyer expansions. There was a point where we wrote nu of m is equal to integral 0 to w square root of m square minus 1 dw by w. This w was our local velocity field vector value. We wrote this, and this in converted to Mach number came to our standard expression 0 to m square root of m square minus 1 divided by 1 plus gamma minus 1 by 2 m square d of m by m. Okay. And we integrated this to get our Prandtl-Meyer function. Okay. But I want to use this expression now, because this is exactly the same expression sitting here, where we said w is our local velocity vector magnitude. This is also the same thing, capital V is our square root of u square plus v square. So, that is also local velocity vector magnitude. So, this is the expression that is sitting here, which means derivative of this nu will be without this integral, this whole thing, right. So, I am getting to a form where this expression, which is exactly same as this expression, is equal to d nu. Okay. So, now my differential equation comes down to extremely simple differential equation, d theta equal to plus minus d nu. There are two differential equations here. I have to write immediately for dy by dx equal to tan of theta plus minus mu. So, if I have a theta plus mu, then I will use d theta equal to plus d nu. If I have a theta minus mu, I will write d theta equal to minus d nu. This is what I will come up with. Okay. So, what we have essentially done after this whole analysis, this is the end of our serious math sections. Okay. What we have come up with finally is two differential equations which are valid along some particular characteristic directions, which are tan of theta plus mu and tan of theta minus mu, where along each of those directions there is one of these differential equations valid, and the differential equation is extremely simple, first order simple differential equation, right. You brought it to an extremely simple form. Integral of this is very simple. Okay. So, we will write the integral form finally. We will say for dy by dx equal to tan of theta plus mu, I am going to say theta minus nu equal to constant. Okay. And for dy by dx equal to tan of theta minus mu, we have theta plus nu equal to constant. These are the main results which we will use for 2D method of characteristics. Whatever we have derived till now is 2D, steady, isentropic, all those irrotational, that kind of flow field. And you get to two differential equations which are valid only along some specific directions. This is what we will end up with finally. Okay. Now, what are its implications? Now, I look at it from x y coordinate system. We have dy by dx here. I have x y coordinate system, and let us say I pick some point in the flow, some random point x1 y1, and I am going to say it is having a flow velocity vector this direction, which means it is having some theta value. Okay, the flow velocity vector has a magnitude of capital V and the direction is theta from our reference axis x. And now I am going to say there are two special directions which are having slope tan of theta minus mu and tan of theta plus mu. This is theta, theta minus mu, let us say mu is different from theta, that is going to go somewhere like this. This is one line, and another line same angle the other side, which will be going something like this. Both are mu angle with respect to the velocity vector direction, and now I am going to say theta plus mu, that is the top line, is going to have theta minus nu constant, and this one will have theta plus nu constant. Okay. Those are special informations carried along this line. That information does not change, it just keeps going along like this. Okay. Similarly, it is going to go along like this, it is going to be this value here. This is what is happening in here. Now, we label these characteristics something. Okay. Typically, the one with positive mu is called the positive characteristic. Okay. This is called the positive characteristic, and this one is called the negative characteristic. That is one way of writing it. But this becomes confusing in problems which are not having almost flow parallel to the axis. There will be problems where things get complicated. So, we have another convention. People use both interchangeably depending on what you are discussing. Okay. I can also have another case where I put myself on this fluid element sitting there locally, and if the fluid element is moving this way, to the right of the fluid element this characteristic runs. So, this is called our right running characteristic, and the other one is called the left running characteristic. That is another name given to it. That is, if I am the fluid element going like this, there is a wave that is running along. I did not give you the word wave yet. There is a direction which goes to the right of me while I am moving straight like this, and there is another to the left of me going this way. If you are looking from the top, that is the picture you will see here. Okay. So, That is what is written here. This is our right running and left running characteristic. Okay. So, now we have defined whatever is happening. What all have I used here? I have already told that it is m greater than or equal to 1, okay. Cannot be less than 1. If it is less than 1, I cannot define my dy by dx. We found that square root will become complex. So, it is not a real dy by dx. There is no real direction along which I can decouple my equations. Okay. But if it is m greater than 1, definitely I can decouple my equations to two different equations which have this solution, the integrated form of the differential equation. You get to this particular form. Okay. So, what is the connection between this and our already existing understanding of gas dynamics? If I think about it, now I have to give this connection of Mach-Kohn and this. You have seen this picture before, where we are saying there is a fluid element that is going along this direction, there is a specific cone or a region inside which the flow will be having influence of this point, right, and that happens to be this region, exactly this region, okay. And if there is a point here, this point does not have any influence on it, or this point does not depend on this point, okay. That is what we are ending up with. So, now math is coming up and telling you that our analysis matches with what is happening physically. We have been thinking physically for some time. At the beginning of the course, we were just telling Mach-Kohn based on whatever we feel physically from acoustic wave propagation, etc. Now we are going and solving it equation wise, and it is also telling you exactly the same thing, okay. So, our analysis seems to be matching in multiple ways, okay. But if you think about it, in olden days when people did not understand this very well, they followed the math first, then from there they got the physical understanding which I gave you at the beginning, okay. You should know that it is a cycle, keeps going up and down. Anyways, the math got us to this point anyway, thinking about it. Now we have to think about one more thing. Supersonic flow, we said, depends only on upstream conditions and not on downstream conditions, right. If I think about one particular stream tube, the flow happening downstream depends on the upstream and not depend on downstream. It may depend on the side of the stream, okay. It does not depend on downstream conditions. That is all I am going to say, okay. Is that shown here? It is not very clear yet. We will wait for one more discussion and then we will come back to this, then it will become more clear, okay. So, we will think about currently whatever information is here. Typically I am going to think about, at this point I know all flow properties. How many flow properties do I really need to know for this problem? Ideally in gas dynamics typically it is 2, okay. But we got this thing, where are those two constants, two numbers that specifically talk about this point? I can think about theta and nu probably at this point. That is one way of looking at it. Typically people use theta and Mach number, because once I get Mach number I can get this mu easily. Of course I have nu, from there I can get Mach number and get mu also. Typically people store theta and Mach number at every point, okay. That is how typically people work with in method of characteristics. Now if I want to find another new point, say I want to find a point on this, say this point I want to find, how will I find the value there? I need to find a theta and Mach number there at that new location. How will I get that? I know one relation between the theta and Mach number there. What is that? Theta plus nu should be the same value as theta plus nu at this point. But that is not enough, I need one more. Where am I getting the other one? Now we go back and think about the zone of dependence, right. This point depends on the upstream cone this direction, right, these two lines. So I am going to say I need one more point given on this, maybe I will use a star here, one more point given on this line of dependence, where this is going to tell me another theta, this is what characteristic? Typically if the velocity vector is like this and this characteristic is coming from this side, it is a left running characteristic. Left running characteristic will have theta minus nu as a constant. But remember, this theta and nu or this theta and Mach number need not be same as this theta and Mach number. Okay. So I will put a theta prime and nu prime there. So theta prime and nu prime, and I am going to say this is going to set a condition on the difference between theta and nu on this point x, while this is going to set the summation of theta and nu at this point. Summation and difference will now be fixing the exact value of theta and nu at that point. Okay. That is how we can calculate another point on this flow field. Now we will go back and look at our previous statement which we were waiting for, which is we said supersonic flow depends only on the upstream conditions. Have I used that here? Yes. This point was found from two upstream points. How do I know it is upstream points? We already assumed the velocity vectors to be like this. One velocity vector like this, one velocity vector like this. Based on these 2 points, I got this point. So I am thinking about upstream point calculated, upstream points used to calculate the downstream point. That is how I am getting to the new point. Okay. If I want to find another point on this, I may need another point from here sending a characteristic this way, right running characteristic, and that will give me another point out there. That will become my downstream point. Okay. So if you are clear with all this, the next step is for me to talk to you about how to write a set of algorithms which you will need to write any method of characteristics solutions problems. However you want to say calculate flow around a body with method of characteristics, or you want to calculate flow through a nozzle. Okay. Those kind of problems, if you want to solve those things, you need to have some set of standard routines, subroutines which you need to have. Okay. So let us look at one by one. Oh, by the way, there is one more thing which I forgot to talk to you about. This whole set of differential equations we used, we did not use the energy equation. I told you that time that I will talk about it later, right. There were 2 things I wanted to talk to you about. Long time back at the beginning of the course, we said if I use isentropic relation mass momentum, I do not need to use energy equation. Okay. Hopefully you remember that somewhere. I said energy equation becomes redundant somewhere. So somehow I have used it inside, but if I want to think about it again, in our case, if I want to think about to find temperature, how will I find temperature if I know Mach number at that point? I still need to calculate some more things, right. If I know velocity vector value and magnitude, velocity vector value and the theta, or I know my m and theta I said, right. If I know m and theta, I actually can find out from here u and v given temperature, but temperature depends on Mach number. So I should be given T naught at that location for me to find based on that particular local Mach number what will be the u and v values. Can I find pressure yet? From here, no. I still need to be given P naught at that local point, so that I can now use this m to find the local pressure. And once I know these variables, I can find every other variable present. Okay. So now I can find density if I want, entropy if I want, all those can be obtained after this point. Okay. So that is why we listed all the primary variables, and then we went in a particular direction where we ignored one equation, and that equation comes up finally here. How will I know P naught in my flow field? We assumed something about the flow. We assumed the flow to be isentropic, and because of that we know that P naught is a constant, right. Isentropic flow, we had this derived long back, delta S by R is log of P naught 2 by P naught 1, right, and if delta S is 0, P naught 2 is equal to P naught 1, that is P naught is a constant. This was already assuming that T naught by T naught 2 by T naught 1 was 1. Okay. If that is not the case, of course you are going to have entropy rise anyway. We had a full expression in terms of T02 by T01 and P02 by P01. Hopefully you remember that it went something like delta S by R is equal to log of T02 by T01 to the power gamma minus 1 by gamma or something multiplied by P02 by P01, some such expression we had. Okay. And if I now say my problem is isentropic, then now I can link that T02 by T01 is 1 and P02 by P01 is 1 for every point across from one point to other always. If I say that, then now I am going to say T0 is constant also. Given these conditions, I can now find every point in the flow as long as I can find theta and m at every point in the flow. So typically method of characteristics people, when they solve, they will just solve for theta and m at every point in the flow, and then they just do post processing of this data to get all these values if they want. That is what they do typically. Okay. In case there is a shock, T0 does not change, but P0 may change, right. We know how to take care of that P0 jump, but remember I cannot have subsonic flow to be solved by method of characteristics. So I cannot have a normal shock in my flow and I want to still solve it with method of characteristics, that is not possible. But if there is an oblique shock and the flow downstream is still supersonic, I can use this as long as I take care of this P0 drop. After that line I will change my P0 to be some other value and continue, then I can still solve this. That is the only way I can take care of this. Okay. Now we will go and look at individual ways of doing things. The first subroutine we want to talk about is interior point subroutine. Okay. If you are writing a program, you need to write these subfunctions, you keep it ready. Okay. The interior point subroutine is basically whatever we just discussed. I am given point A and point B, and when I say I know points A and B, I have to write here point actually means I know the x location, the y location, the theta at that location and the m at that location. I know those 4 properties. If I tell I know a point, then only I fully know the point. Okay. Now from this, given A and B, that means I know a x, y, theta and m at each of these points. Now I want to find another point C. Okay. This is the most used subfunction in method of characteristics. Okay. This is what fills your whole interior of the flow. That is why it is interior point anyway. Okay. This is, all these points are inside in the middle of the flow, not near a wall or near a jet boundary, etc. It is inside of the flow. Okay. So we are given these and we want to find this point. We are given x, y values of this, theta, m values of this. So what should I do? Let us say velocity vector is like this, velocity vector is like this. I do not know what values it will be, some values arbitrarily. Now I am going to say I have drawn a right running characteristic or a negative characteristic from A, which means I will have theta plus nu is a constant on this line, and on this line it will be theta minus nu is a constant on this line. Positive characteristic will have theta minus nu constant. Okay. I like to think about it as positive and negative. It makes sense when I want to use the opposite sign in theta plus nu versus theta minus nu. If I say it is a negative characteristic, it will have theta plus nu constant. If it is a positive characteristic, then it will have theta minus nu constant. That is why I prefer to use positive and negative. But it will get confusing after some time and angles are not going to remain positive or negative. Okay. There it will help if you have left running versus right running. Anyways, now how will I solve for this? Simple thing, I already told you how to solve for this theta c and nu c. Those are your unknowns for this, right? I do not know theta c and nu c. I also do not know x at c and y at c. First we will look at theta c and nu c, easy to look at. We know theta a and nu a, we know theta b and nu b. So I can just go and write theta c plus nu c is equal to theta a plus nu a. And from line BC I can get that theta c minus nu c equal to theta b minus nu b. We know the values on the right hand side, we do not know the left hand side. Average adding these two and dividing by 2 will give me theta c. First one minus the second one and dividing by 2 will give me nu c. So, I can easily get theta c and nu c. Okay. So, I have solved the flow properties at that point C. Now, we want the exact location of the point C. Okay. Let us think about that part again. I will draw fresh drawings. And this velocity vector will be something else. Okay. Now, I know that this characteristic line need not be a straight line always if I think about a bigger flow field. Okay. If it is a bigger flow field, depending on the flow direction, locally that particular theta and mu tan of theta plus Mach angle, that will decide my left running characteristic. And at this point, if the Mach number and theta are such that it is going to change, the characteristic may still turn, it may keep turning like this. Similarly, the other characteristic may turn like this, whatever, it may do different things. If I think about it from this perspective, I have one point here and I want to find this point, this is the other point. If I just use the slope from here and extend it, I may reach somewhere else. Similarly, if I use the slope from here, I may reach here instead of this point. Okay. But with the given information, how close can I get to the actual point? That is what we want to think about. So, the simplest approximation, if I do not worry about too much errors, then I will just do the silly thing. I will just assume, let us say this is my A and B points, right, A, B points. I am going to assume that from here my characteristic is running as a straight line up to this point. Here it is a straight line. So, I can just go ahead and write tan of theta A minus mu A is my dy by dx of AC, and similarly dy by dx of BC is equal to tan of, this is a positive characteristic, theta B plus mu B. I can write like this. This will have some errors if the flow is not very uniform. If the flow is very uniform, this is enough. If you already know beforehand that the flow is not going to have so much of change in characteristics, then I can just go ahead and use this is enough. But if there is too much change, then I am putting the value that is supposed to be here, that is the theta and nu values which are supposed to be here, now I am putting it there. That means I am already off on where the data should be written. Okay. To correct for that, with the data available, the only thing we can do is, we will take an average of the slope here on the curve. There is a slope here. I need to draw it again. I will draw it here. I am taking one slope here and one slope here for the same positive characteristic, and I am going to say I will take an average slope between this value and this value and put that as the slope for this line. Okay. If you go do numerical methods, you will find that I am approximating this curve to be a parabola at that point. Okay. Instead of it being a straight line which is this, I am assuming it to be a parabola at this point. I am interpolating in slopes, which means it will become parabola. That is the idea. Okay. It will basically, I am using the slope here at the midpoint as the slope of this line. That is what I am doing really. Okay. I am using the slope of this point here. If I use this, this will give me a closer approximation. It will not be very, very bad. That is the best we can do because that is all the information we have in this. So, what we do is, instead of this version of dy by dx, we will write it different. Dy by dx of AC, AC is my right running characteristic. So, it is theta minus mu. I will write tan of theta A minus mu A plus theta C minus mu C divided by 2. I will write it like this. I am taking an average of the angles and then putting a tan of that. Do I actually know the values theta c and mu c? Yes, I can know it because I already have this equation which can be independently solved of it. So I know theta and mu, so I can use theta and mu here easily. Similarly, I will write dy by dx at BC tan of theta b plus mu b plus theta c plus mu c whole divided by 2. I will write it like this. Okay. Of course, you will see different books writing it differently. Some books will write theta b plus theta c by 2 plus mu b plus mu c by 2. It is the same thing anyway. You can look at it whichever way, just different groupings. So, if I have a subroutine for an interior point, I am given x, y, theta m for 2 points A and B. I need to get x, y, theta m for C. How will I do it? I will start with solving for theta c and mu c. Immediately after that, I will use these two expressions. I will draw straight lines from A and B, these 2 points, and now I have to write another subroutine for 2 lines intersecting with some particular slopes and particular points, solve for the point of intersection. Have that code also ready. Okay. If you have that silly subroutine, you will get the xy locations of this point C. So that is all I need to do. I need to have an intersection code, intersection simple subroutine, and then I need to have an interior point subroutine which will call that thing after this calculation. Okay. Once I have this, I can calculate most of the points in my MOC, in my flow field, except for a few. So we will need some more, we will give some more. So what if my flow field is near a wall now? I am looking at some point near a wall. So we will write a wall point. I will tell you how to use all of them together probably next class. Okay. Wall point, that is, I am given a point A and there is a wall somewhere nearby, and there is no other point here, no more interior points. Okay. I have this. So flow is going like this, and I am going to say there is a right running characteristic for this reaching here to this wall. I need to find properties at this point B. This could be one situation, or an equivalent situation will be there is a wall on the top side and there is a point here A, and now I need to find this point B. Both these situations can arise. If you are thinking about flow through a nozzle, both of these can arise. Even flow around bodies, both of these can arise. Okay. In such situation, we want to find how to solve this, how to solve for the point B. When I say solve for the point, I mean we need to find the location and theta and mu for that point, okay, theta and Mach number for that point. So how will I solve it? Immediate thing you should know is wall enforces velocity parallel to it, okay, which means at this point B, immediately theta B is known. Theta B is equal to theta wall. What is this equal to? Tan inverse of dy by dx at that wall, at that point. But of course, I do not know the point yet. Hey, this may be a curve and the slope may change from point to point. I do not know the exact point, but I can find slope at any point. So I can find theta at any point. Okay. The next thing you have to think about, if I know this, if it is a right running characteristic, theta plus nu is a constant. This is one case, or I could have the other case, 2 cases, right. The other case could be parallelly, I will write for the other case here, probably I will, just to be very clear, I will use C and D here. so that they are two separate cases. I can also write parallelly theta c minus nu c equal to theta d minus nu d. I can write this also, right. If it is a right running characteristic or a negative characteristic, then theta plus nu is a constant. If it is a positive characteristic, then theta minus nu is a constant. Depending on what hits the wall, your subroutine should adjust that slightly. Okay. So, your subroutine can have two parts, or you can write two separate subroutines, wall for negative characteristic, wall for positive characteristic, something like that. Okay. So, now what is the unknown here? Only unknown is this. So, I can find it directly, everything else is given, assuming you already know the location on the wall. Okay. It is not really known. Now, we will go back and look at how to find this point. We can think about simple iterative procedure, which is I am going to think about from there. First, I will just send a straight line with dy by dx of AB is equal to tan of theta minus mu here, theta A minus mu A. I can just send this. This is I am taking into account only theta and mu from this point, not an average between these 2 points. I will just take the first one alone, and from there I will just go and write this expression here. That is one way of doing it. If I do this, if the wall is curved a lot, I will have a lot of problems. I will give you an example case. My wall is curved like this, and my characteristic is curved like this, and currently my point A is here. If I have such a situation, if I just use the slope from here, I am going to meet this point, which is actually having some other slope here. So, this will have more errors. So, what will I do? First, I will do this. For the next iteration, I will just go through this iteration till it converges to some reasonable accuracy. What I will do is, first iteration I do this, second iteration, this is first iteration, second iteration I am going to write dy by dx of AB is equal to tan of theta A minus mu A plus theta B minus mu B divided by 2. I am taking an average now, and I will keep on doing this step 2 till I am getting dy by dx exactly the single value. How will I get to all these points? I am assuming a lot of things probably in this routine. The way to solve it, first I have to go and use this. This is the first thing I need to do in my routine, step 1. I will use this dy by dx. Now, I need to have a routine which gives me wall curvature versus this line intersection, function of the wall and function of this line intersecting point I need to find. I will find the point where this line intersects the wall. I need to have a routine for that. After I get that, once I know that point exactly, I can now tell dy by dx at that point. From there I get theta b, I will put that in here, I get nu b. Now I know theta and nu or theta and Mach number at location b. Once I know that, I can go and use it here. Theta b and Mach number will give me Mach angle. Okay. Theta b and mu b I can use. Once I know this, I can get a new value for dy by dx. Previous value for dy by dx is now discarded. I will get a new value. Go through the same thing, I will get another new value. This time it will be closer to the previous one. I keep on doing this till it will converge automatically. Okay. It will come to some value, within some accuracy we will stop. Let us say if it does not change more than 1%, I will stop, something like that. We will keep on doing this. Similar thing for that, it will be all this theta minus mu will become plus mu there. That is the only change. I will write here step 1 dy by dx for CD is equal to tan of theta c minus mu c, and for step 2 dy by dx of CD equal to tan of theta c minus mu c plus theta d minus mu d whole divided by 2, an average of those two, and this one keeps cycling across. You keep doing this several times. Step 2 is just done till you converge to slope does not change more than 1% kind of condition. Okay. And finally, that gives out your point B or point D depending on whether you are having right running characteristic hitting the wall or left running characteristic hitting the wall. Okay. And this gives you the next point. Now, the other ones are with this most of the problems can be solved. Okay. If you are thinking about simple flow problems like say a flow through a duct, I still did not talk about one particular thing. Somehow you know some array of points which I have to talk about next class. Okay. If I know a lot of points here, now all I have to do is take this point, the topmost point, find the wall point, CD based wall point. From here I will send AB here based wall point in here, all the other characteristics interior point. So, I have basically advanced my data by one step forward, that will form my new line here. From here this last point is already on the wall, so there is no more line going to the wall. From there it is only interior points. That forms one more level of data, and like this I can keep on going. The next time it will go to the wall, here also it goes to the wall. Now I have data for one more layer, and like this I can do this forever. So, I can solve flow through a nozzle using this itself, except for you need to know this very first line of data, somehow it has to be given to you. We will talk more about this next class.